nucleophilic substitution reaction. Okay. So when a nucleophile is replaced with the another nucleophile, it's said to be nucleophilic substitution reaction. So basically the ability of donating tendency of electrons is said to be nucleophilicity. Okay. So that we discussed in the last class. Okay. So nucleophilicity is what? The tendency to donate the electron density. Okay. The tendency to donate electron density. So if it is more effective nucleophile or more tendency to donate the electron density, then it is said to be a strong nucleophile. Okay. When it is not able to donate the electron density, then it is said to be weak nucleophile. Okay. So strong nucleophile and weak nucleophile. Okay. So in a period, okay, in a period, for example, if I take chlorine, bromine, and iodine, okay, the nucleophilicity depends on the electron density. Okay, so what is meant by electron density? The tendency to hold or attract the electron pair towards itself. Okay, attract the bond pair. So it is a electron holding capacity. Okay, so when it is having more electron holding capacity, it cannot donate more. Okay, so in a period, the nucleophilicity will be going to increase as the electron activity is going to decrease. Okay, so iodine is a good nucleophile when compared to the chlorine. Okay, so nucleophilicity, sorry, in a group. Okay, from top to bottom in a group, it's going to increase. Okay, in a period from left to right. Okay, for example, carbon, nitrogen, oxygen. If I take the nucleophiles of these, it's going to decrease because the electron activity of the element is going to increase. Okay, in a period, it's going to decrease from left to right because the electron activity is going to increase. Okay. So this is about the nucleophilicity that we have discussed in the last session. Okay. Now we are also need to know about the solvents. Okay. So that in nucleophilic substitution reaction, either the nucleophile or the solvent is going to direct the nucleophilic substitution reaction with a different kinetics and with a different mechanism. Okay. So if you know about these types of the solvent, then it will be possibly to understand the nature of that particular reaction. Okay. So solvents based on H plus donation tendency. Okay. H plus donating tendency are two types. They are protic solvents and aprotic solvents. Okay. Protic and aprotic solvents. Okay. Protic means which can form hydrogen bond or which can donate H plus are said to be protic solvents. Okay. So this is called hydrogen bond donor solvents. Okay. For example, you can take water and ammonia and any alcohols. Okay. And HF. You can also take carboxylic acid, which can also have hydrogen. Okay. So literally you can say hydrogen having solvents. Okay. H plus having solvents. They are protic solvents. Okay. Aprotic means which cannot form hydrogen bond. Okay. The solvent which cannot form hydrogen bond. Okay. So they are said to be aprotic. These are not hydrogen bond donors. Okay. For example, benzene, okay, acetone, and hexane, okay, and DMF, dimethyl sulfamide, sorry, DMF, dimethyl formamide, okay. So this is pharmamide and non-veg methyl. Okay. DMF, this is also solvent. DMSO, dimethyl sulfoxide. Okay, this one. So 2 methyl and sulfoxide. Okay. So and all ethers, these are aprotic solvents. Okay. So why we are looking into the details of these solvents means you will be given a reagent which can act as a nucleophile and you will be given the solvents which are going to direct the reaction. So based on them you need to identify whether the reaction is going to give what type of mechanism. Okay. So this is based on the H plus donor. Okay. Next, protic solvents. Okay. Sorry. Protic, aprotic is known. Polar. Polar solvents and non-polar solvents. Okay. Polar and non-polar. So when it is polar solvent, they have high dielectric constant. Okay. High dielectric constant. Okay. High dielectric. If it is non-polar, they have low dielectric constant. What is dielectric constant means? Or what I mean polar is when you take water, okay, which can form H plus and OH minus. Okay, the molecule which can form into two poles are said to be polar molecules. Okay, so here electrical charge difference between these two will be maximum. That is called dielectric constant. Okay, so if the dielectric constant is high, then they are said to be polar solvent. For example, H2O, its dielectric constant will be 78. Okay, and formic acid, it will be 80. Sorry, it will be 60. And DMF, it will be 37. Okay, DMSO, it will be 47. And ethyl alcohol, it will be 35. Okay, so when the dielectric constant, okay, is more, they are said to be polar. Okay, so solvents can be polar protic and polar aprotic, non-polar protic, non-polar aprotic. So this is a type of classification which based on the H plus. This is a type of classification which based on the polarity. Okay, so both are different, both are individual. Okay, so if I take H2O, it is a polar protic solvent. Okay. So if I take DMSO, it is a polar aprotic solvent. Okay. So next is non-polar solvents like benzene. Okay. Uh, which has the dielectric constant 2.3 and N-hexane which has 2.0, CCl4 means the molecule is very much symmetrical. Okay, so it shouldn't have any charge difference between the molecule. Okay, the polarization is not going to happen in the molecule. They are said to be non-polar. Okay, so their dielectric constant will be very less. So CCl4 and CHF 7.5 and chloroform, it is 4.5. Okay, so make a note of every solvent and everything. Okay, because these are going to useful. Okay, to identify whether the given reaction is undergoing in polar solvent or non-polar solvent, in protic solvent or aprotic solvent. So this is for the lifetime chemistry observation. Okay, so not just useful for now. Okay, so you should able to identify the solvent based on that. For example, what is the importance? If I mean to say, let's say in a reaction, if the H is there, it's going to form the final product. Okay, so This is a anion, okay, that is going to generate in the reaction, and if H plus availability is there, then it's going to form methane, okay. If not, it's going to available as such, okay. So if this is the condition, if I give a protic solvent, you must write a CH4 as a final product. If I give an aprotic solvent, there won't be available of the proton, so you must write CH3 minus as such, okay. So that is the important. Based on that, this is just a criteria I am giving. So based on the protic solvent and aprotic solvent, the hydrogens that must be attached for a product or the final product can also be defined, and the mechanism can also be there. Okay, so make a note of this. Okay, or take a screenshot and preserve it. Okay, so it is going to useful for next classes and for identifying the different kinds of the reagents. Okay. So next, we'll be going to see the typical nucleophilic substitution reaction. Okay. So when it is alkyl halide or any leaving group, any nucleophile, if it is treated with the nucleophile, okay, it is going to give the product by the nucleophilic substitution reaction. Here we are going to use the solvent. Okay, solvent. So if a nucleophile is different, that is going to attack. Let's say I am using OH minus. What could be the product? It will be ROH. So based on the nucleophile that is going to use, the product will be defined. Okay. So here I am giving the particular examples of nucleophile and the product. Okay. So this is what nucleophile that I use for the above reaction and the product that I got. So if I use halogen as a incoming nucleophile, so what could be the product? I am going to get alkyl halide. Okay. If I use H2O, so it's going to give its OH minus, so it will be ROH. If I use OH minus also, it's going to give ROH. Okay. In H2O also there will be a OH minus or simple OH minus like base. Any OH if I take, so it is also going to give alcohol. Okay. If I take alkoxide RO minus, so then I am going to get ROR, which is the ether. Okay. So if I take carboxylate anion, okay, so this is going to attack onto the iron, so it's going to do ester. Okay, ester. So if I use phenoxide, so it's going to do phenoxy ethers, ROPH. Okay. If I use ammonia, so it is NH3 means NH2 minus and H plus. So it's going to give R NH2. Okay. I can also take the NH2 minus. Okay. So this is also going to give R NH2. Okay. So some more nucleophiles and their products. When I take azide, this is azide, make a note. Okay. Write the name. When I take azide, so it will be alkyl azide. Okay, alkyl azide. When I take nitro anion, it's going to give nitroalkyl. Okay. When I take cyanide, it's going to give alkyl cyanide. When I take hydrogen sulfide, so what it could be there? H plus and HS minus. Okay, like OH minus. So it's going to give thioalcohol. Okay. So when I use thioalcohol itself, okay, so it's going to give S R minus and H plus. Okay, so this is minus, this is plus. So it's going to attack. So it's going to give thioethers. Okay, this is thioethers. You can write down the name also. Okay, so if it is RS minus. Okay, so thioalkoxide. Okay, thioalkoxide. Then also it's going to give thioether. Okay, so Next, these are little important. If I use KCN or NaCN, which are ionic cyanides, okay, ionic cyanides, then it is going to give alkyl cyanide, okay. When I use AgCN, which is covalent cyanide, okay, covalent bond, so attacking will be from this side, okay, so it's going to give isocyanide, okay. These two are very important, okay, as a nucleophilic substitution reaction. So this is the table that is going to give almost, here I included almost 20 nucleophiles. So you can make 20 different reactions, nucleophilic substitution reactions. If you are going to change the starting material, it may be many, like hundreds of reactions are possible with these data. Okay. So this table is very important. So try to write or try to copy the table. Okay. So because each nucleophile is going to give each different product. Okay. So next look into the types of reactions of nucleophilic substitution. So generally based on the molecularity. So here I am giving, okay, so types of nucleophilic substitution reaction. Okay. So based on the molecularity of reaction, it is defined as a SN1 and SN2. Okay. You might be wondering from intermediate. Okay. So what is this SN1 and what is this SN2? Okay. So here I will give the realistic view, so that makes you understand very easily. Okay. So SN1 means it is nucleophilic substitution reaction unimolecular, and this is bimolecular, nucleophilic substitution reaction bimolecular. Okay. So where the reaction rate, okay, rate of the reaction, if it depends on the one molecule, that is said to be unimolecular. If it is depends on the two molecules, that is said to be bimolecular. Okay. So what is that one molecule here is, it is starting material, that is what, alkyl halide. Okay. What we are discussing? We are discussing about the nucleophilic substitution reaction. Okay. So in a nucleophilic substitution reaction, if the reaction rate is just depends on the alkyl halide as starting material, then it is said to be nucleophilic substitution reaction unimolecular. If the reaction rate is depends on the alkyl halide as well as the nucleophile, then it is said to be substitution reaction bimolecular. Okay, bimolecular. So to simply understand the mechanism of the nucleophilic substitution reaction, okay, so I will just give in a single way. Okay. Just give me a minute. Here I am going to show a picture where you can understand what is actually nucleophilic substitution reactions and what is their mechanism. Okay. is little bit suffering. Just leave it there. So in this you can find the picture. Okay. So is it visible? So this class also you can find. Okay. So here if it is SN1, so it's like a the center is about the area or the place where the reaction takes place. Means it is the actual starting material molecule where alkyl halide is going to is need to react. Okay, so this is the alkyl halides carbon. Okay, so here halogen is there. Okay, in SN1 after the elimination of this halogen, okay, this is what the halogen. Okay, so incoming nucleophile can take place. Okay, so incoming nucleophile can take place. Okay, in SN2 before the leaving of halogen. Okay, so before the leaving of halogen, this is halogen. Okay, incoming group will push it to leave it. Okay, so incoming group will push it so that it needs to leave. Okay, that is the main difference. Okay, so where the rate, okay, in SN1 will be just depends on the alkyl halide because the rate is the leaving of the alkyl halide. Okay, so rate just depends on the leaving of alkyl halide. Okay, so it is the only one molecule where the nucleophile is away from that. Okay, so here only rate depends on the leaving group, that is what halogen. Okay, but in SN2 if it is push more, okay, if it is he is pushing more, it should be very easy to remove this. Okay, so the rate or speed of the reaction depends on the both. Okay, so when it he tries to leave from there, then also speed of the reaction increasing, and when the incoming group tries to push it, then also reaction is going to fast. Okay, so this is the main difference. Okay, so so this is the best picture that is going to explain SN1 and SN2. Okay, so let's see the mechanism now. So in the mechanism, when you take a alkyl halide and if it is a strong nucleophile, okay, and there can be a weak nucleophile. Okay, so when it is a strong nucleophile, what is going to happen? Before or it will itself very active. Okay, so it won't wait for anything. Okay, so it definitely going to attack on the nucleophile. So now alkyl halide, now it should leave. Okay, now it should leave. So it's going to give nucleophilic substitution directly, okay, without any gap or without any delay. Okay, but where it is a nucleophile, it is less readily active. Okay, so less readily attacking. So as a reaction needs to perform, so this alkyl halide leaves the halogen so that it is going to form the intermediate, okay, the carbocation. Now anyhow this was not attacked by the nucleophile because it hasn't generated any charge. Okay, but now after the generation charge, nucleophile itself is a negative and it should be, it definitely should attract and should attack of the positive, so it is going to attack. Okay, resulting into what? So product. So the basic difference is what? The basic difference is about the strength of the nucleophile. When nucleophile is stronger, it's going to push. Okay, so you can imagine the second picture. Okay, so when nucleophile is stronger, it is going to push. Okay, so that what it is? So it is a SN2 reaction. Okay, so SN2 reaction. So leave the halogen or leave the leaving group which on its own and resulting into the formation of intermediate that needs to attacked by the nucleophile. Okay, so here you can see that. So when it leaves on its own and nucleophile is going to take place onto the intermediate position, okay, or vacant position. So this chair is vacant, that is what intermediate, and that is what carbocation that is generating from the alkyl halide. Okay, so this is what the intermediate, and this is what empty chair. Okay, so alkyl halide. Okay, so carbocation that is. So this is called SN1. Okay, so basically the SN2 reaction will not have any intermediate, so it is going to give in single step. Okay, so that is why it is called concerted reaction. Okay, so concerted reaction means where there is a where there is no intermediates. Okay, no intermediates. Okay, so when it is non-concerted, then it can be intermediate. Okay, so this is step 1 and this is step 2. Okay, so it will be in 2 steps. Okay, 2 steps. SN1 will be in 2 steps. Okay, so what is the main driving force for the SN1 and SN2 differentiation? The main driving force reactivity. Okay, only reactivity of what? Nucleophile if it is more reactive, or in other way, if the alkyl halide itself is more reactive, okay, then it may be into it may change the reaction types. Okay, so if the strong nucleophile is there before the leaving of halogen or before the leaving of leaving group, if the nucleophile attacks, it will result into the SN2. Okay, so after the leaving of leaving group, if a nucleophile attacks, it will result into the SN1. Okay, so the leaving of the leaving group is slowest step in this reaction. Okay, so it is called rate determining step. Okay, so generally the slowest step is called rate determining step, because if a reaction is going to take 99 minutes, okay, and this going to take up in 1 minute. Okay, so the most of the time, if you are looking at the reaction, the main or the happening will be with this step only. So that's why it is called rate determining step. If it is decreases by 10%, then it is going to give in 90 minutes only. Okay, if it is decreased by 10%, then it will be 0.9 minutes. Okay, so where is the maximum difference? So which you consider as a fast reaction or most change in the rate. So this is what. Okay, here 9 minutes are going to change. So comparatively it's going to be very faster when you are changing the rate or changing the speed of this step. Okay, that's why it is called rate determining step. Okay, so the rate determining step, in the rate determining step, the rate of the reaction just depends on what? The alkyl halide. If the alkyl halide readily leaving the halogen or leaving group, then it can be faster. If the alkyl halide does not able to leave the halogen, then it can be slower. Okay, so rate is directly proportional to the concentration. If the more the alkyl halides are there, you can find more reactivity. Okay, if the alkyl halides concentration is less, then you can find less reactivity. Okay, so rate is proportional to the alkyl halides only. If I increase the nucleophile concentration, so what is going to happen? Nothing is going to happen, because nucleophile is going to happen in the second step. So if I increase the nucleophile, it may change from 1 minute to 0.9 minutes. That may not be considered as a change, as a considerable change. Okay, so here in the SN1 rate is directly proportional to the concentration of alkyl halide. Okay. So, but in this, if I increase the concentration of the nucleophile, more number of the nucleophile is going to attack. Okay. So, more faster the reaction is going to happen. Okay. If I increase the concentration of alkyl halide, more number of alkyl halides will be available for the attacking of the nucleophile. Then also reaction will be going to faster. Okay. So rate is depends on the either alkyl halide concentration and as well as the nucleophile concentration. So the rate is depends on the two molecules. That's why it is bimolecular, and this is a nucleophilic substitution reaction. So it is SN2. Okay, the rate is depends on only one molecule. That is what starting material, and it is a nucleophilic substitution reaction. That's why it is SN1. Okay. So this is about the nature of the two reactions based on the type of the nucleophile. Okay, strong and weak. Okay, weak nucleophiles always give SN1 and strong nucleophile always give SN2. Okay. Now let's see in detail about the starting material. Okay. So if the starting material is methyl halide and starting material is tertiary butyl halide. Okay. So if it is broken into the carbocation and the halogen, and if this is broken into the carbocation and the halogen, so considerably the tertiary butyl carbocation will be much more stable when compared to methyl carbocation. So the breakage of this bond will be more readily going to happen in the tertiary butyl system. Okay, tertiary carbocation generation. Okay, so this is going to give intermediate faster. Okay, this tertiary alkyl halide is going to give intermediate faster because the intermediate is going to be tertiary carbocation which is more stable. Okay. So intermediate formation is a major step in the SN1. Okay. So whenever it is the alkyl halide which is with tertiary, then it is predominantly follow the SN1 mechanism. When it is alkyl halide which is primary alkyl halide, then it will not stabilize with the carbocation that is forming. So it will be predominantly follow SN2. Okay. So what about the secondary? Secondary may give SN1 and SN2 based on the nucleophile. Okay, based on the nucleophile. Okay. So if the reaction in the reaction, if it is a strong nucleophile and secondary alkyl halide is there, then of course it needs to be attacked before the alkyl halide halogen leaving is going to take place. Okay. So then it is going to be SN2. If the weak nucleophile is there, halogen is going to break up, carbocation is going to generate, and it is going to follow SN1. Okay. So this is about the starting material criteria, and this is about the nucleophile criteria. Okay. So next we are going to see the solvent. Okay. So if the solvent, if I use polar, so what is meant by polar? Where the positive and negative poles can generate in the solvent. So like H2O. Okay. So it can form H plus and it can form OH minus. Okay. When it can form H plus and OH minus, when alkyl halide is there. Okay. So this X minus is going to attract towards the H plus and OH minus is going to attract towards the positive. Okay, so what is going to happen? It is deviating the bond. Okay, so it is also generating the poles between the molecules of the starting material. So how it is going to happen? It will break itself into the ions. Okay, it will polarize the starting material also. When polar solvents are there, it will polarize the starting material. So when polarization or ions generation is going to happen, what is the mechanism it should follow? It should follow SN1. So in SN1 it should be polar solvents. Okay. In SN1 it should be polar solvents. Okay. So next in non-polar solvents. So non-polar means the bond breakage or bond polarization will not happen. So when bond polarization is not going to happen, then nucleophile must attack onto the alkyl halide so that this leaving group should leave. Okay, so it is following the criteria of SN2. So for SN2, it will be non-polar solvents. Okay, so this is about the solvent criteria. Okay, so that's why I have given polar and non-polar solvents. Okay, so when polar solvents are there, it's going to ionize. Okay, it is going to ionize. So ionic reaction mechanism will be SN1. When it is non-polar, so it is non-ionizing. So the reaction will be SN2. Okay, so this is about the SN1 and SN2. Okay. So next, if I take a chiral molecule, what is chiral molecule? Okay. So this is chiral molecule. The carbon compound with or the center of carbon which is having four different groups. Okay. So these are optically active, means they're going to rotate the plane polarized light with a different angle of incident. Okay. So when a chiral center or chiral carbon is there, okay, they are optically active. Okay. So when this is treated with the uh, nucleophile, okay. So if it is following the SN2 type, okay. So let's take SN2 type means it should attach, okay. It should attach. So this is what halogen which is with lone pair. So this is what nucleophile which is with negative charge. So when it is approaching directly, it should not happen because these two are going to repulse each other. Okay, these two are going to repulse each other because they are having negative charge with each. Okay, both are negative, so it shouldn't attack from this side. So it is going to attack from the reverse or anti side. So it should leave. Okay, so it should leave. So it should result into the inversion. Okay, this chiral center is towards this, so it should change its configuration into the reverse. Okay, so resulting will be the nucleophile here and C2H5 here and CH3 here. Okay, so it will reverse the chiral center's configuration. Okay, so it will reverse the configuration. Okay, that is said to be inversion of configuration. Okay, which is observed by the Walden. So this is also called Walden inversion. Okay. So generally the chiral centers are named with the R and S nomenclature or plus or minus nomenclature. Okay. So when it is optical rotation is positive, it will be denoted as plus. When optical rotation is negative, then it is denoted as a negative minus. Okay. So positive means it is rotating the optical light to the clockwise direction. Negative means it is rotating the optical light. Okay. So plane polarized light in the anti-clockwise. Okay. So this is configuration based on the priority groups. Okay. CIP rules, based on the CIP rules. Okay, so these all are defined in the stereochemistry chapter. Okay, that we are also going to discuss. Okay, so when it is R configuration, its reverse will be S. Okay, when it is R configuration, its reverse will be there. Let's say this is R configuration, its mirror image or its reverse will be S. Okay, so this is what the S configured compound. Okay, of the starting material. Okay. So this is what is okay. So when you are taking the R configuration starting material, it is going to result into the S configuration. Or when you are taking the plus or dextro rotatory or clockwise rotatory enantiomer, is going to give minus or levo rotatory, okay, enantiomer. Okay, so that is going to happen in SN2. Okay, when it is in SN1, what is the criteria? It should leave the halogen. So resulting will be the carbocation. Okay. So this is what the carbocation that is generating. So what is the hybridization of carbocation? It will be sp2. So if it is sp2, what is the shape? It will be trigonal planar. Okay. So this is the planar molecule. when in the next step, when it is a nucleophile is going to attack, it can attack from the upper side, it can attack from the downside. Okay, so if it is attacking the from the upper side, okay, and this is not nucleophile. Okay, so and if it is attacking from the downside, okay, so if these two are mirror images, so if I place one on the above the other, so they can reflect each other. Okay, so resulting into what R and S isomers. Okay, so it's going to give enantiomers. Okay, so two enantiomers each of 50% is going to form. Okay, this combination of two enantiomers each of 50% is called racemic mixture. Okay, racemic mixture, which is what optically inactive, because one can rotate the plane polarized light to the right and other can rotate the plane polarized light to the left. Each is going to cancel, so optical activity is going to cancel. Okay, so inactive. So in SN1 is going to give racemic mixture, which is called racemization. Okay, in SN1 racemization is going to happen. In SN2 Walden inversion is going to happen. Okay, these are based on the stereochemistry. Okay, so this is completely stereochemistry of SN1 and SN2. Okay, so this is the complete explanation about the mechanism and the stereochemistry of the nucleophilic substitution reaction, which is very essential and very repetitive in the previous examination. So try to repeat or revise the video again and again, so that you are going to understand every concept and every uh, minute things in the mechanism, so that we can apply in the further reactions. Okay,